Hello everybody, and welcome to Do Math, where this week we'll be taking a look at natural logarithms and a little bit of the calculus around those guys. Okay, let's go in and take a look. All right, so we've got two integrals here. I'm going to do the one on the left first. The integral of x over x squared plus 3 dx. If you want to give this one a shot right now, go ahead and pause your video. Okay, so here we go. Let's do a little u substitution. I'm going to let u be the bottom part here, x squared plus 3. And when I let u equal x squared plus 3, that means the dx is going to be du divided by 2x. Okay, so let's go in and make our substitution. So we've got an x on top, divided by, now the x squared plus 3 is our u, so we're going to replace the bottom with u. And this dx we solved to turn that into du divided by 2x. As you can see, what happens is our x's cancel out here, and we're left with a 1/2 that we can pull onto the outside. And inside the integral is 1 over u du. Now never forget what integrals mean. Integrals, especially the integral sign together with the du, mean, of course, to integrate, to antiderive whatever's on the inside. And that's what we're going to do. You can't forget that. You can't ever just leave integrals alone. When we antiderive this, we'll get 1/2 ln, the absolute value of u, plus c, which is equal to 1/2 ln, the absolute value of x squared plus 3, plus c. It's not like the du is turning into the plus c at all. That's not what's going on here. This does not become that. The integral and the du together mean integrate, and we're integrating 1 over u into 1/2 ln, absolute value of u. So there we go. There's our antiderivative. Problem finished. Good. Okay, if you want to try the next one, go ahead and pause. All right, for this integral, we are going to do another u substitution, only this time we'll let the u actually be ln of x, because I see that in this integral there's a little 1 over x floating around. I don't know if you guys can see it, but it's about right there. And I know that with that 1 over x, the derivative of ln of x is 1 over x, so maybe, just maybe, and by just maybe I mean most definitely, when I derive ln of x, I'll get 1 over x on the bottom, and that will actually cancel things out. So this will end up being du divided by 1 over x is du times x, or dux, as my 4th hour is very fond of saying. And this integral we can transform into, all right, we got 1 over x times an ln of x, that was our u, and then dx turned into du times x. And now what we can see is that the x fully cancels out here, and we are left with the integral of 1 over u du, which is, of course, just as it was over on the other integral there, ln, the absolute value of u, plus c, which is ln, the absolute value of ln of x, plus c. And we are doing this integral because we've got these bounds here. We're going from e to e squared. So we better plug this stuff in right here. So ln of e squared minus ln of e. Now, if you know anything about natural logs and e's, you'll know that ln of e squared on the inside here is just, well, the 2 can clog down and we end up with just 2 minus, and then ln of e on the inside there is 1. So then this just turns into ln of 2, because ln of 1 is 0, and it just sort of goes away. So ln of 2. Good deal. All right, those are some integrals. Let's go on to this. It says find the particular solution to the differential equation through the given point. Now, before you might want to start this, what I would do is just think about what it's asking you. It says find the particular solution. I know you guys haven't seen that verbiage much before, but you'll notice in the problem it gives you a derivative and it gives you a point. Now, like I said, we haven't seen these problems much, but the particular solution through the point probably means that we should antiderive this back up to the function from the derivative, and then we can use that point to figure out the plus c. If you want to give that a shot right now, you can feel free to go ahead. Okay, so I know that if I antiderive this, my function r of t will end up being the integral of this thing. So secant squared over tangent plus 1 dt. And I can accomplish this integral with a little u substitution on the side. So tangent, I'm going to let u be tangent of t plus 1. Yeah, that's going to be good. And then the dx will end up being du divided by secant squared of t. Okay. So let's make the substitution. So that'll end up being the integral. I'm not subbing anything into secant squared. However, my bottom does become u. And then the dt, oh, I'm sorry, I put a dx right there. I meant dt. The dt will end up being du divided by secant squared of t. And now we see that these secant squareds cancel out. And we're left again with the integral of 1 over u du, which by now we should know pretty handily is ln, the absolute value of u, plus c, which if we sub our u back in, should be ln of the absolute value of tangent of t plus 1, plus c. And that's actually what our function r of t is equal to. I know it's r of t because I've got two variables in here. I've got r in terms of t according to my derivative, so r of t. Now if I want to solve for the c, this is the thing that I want to use my point to actually find what c is. That's the meaning of this particular solution verbiage in there. So we have our point, which is pi comma 4. So I know that my y-coordinate is 4. And my t-coordinate will end up being pi. So let's write ln, absolute value, of tangent of pi plus 1 plus c. Now, okay. Tangent of pi, if you think about tangent on the unit circle, tangent is y over x. And pi is on the left hand side of the unit circle over there. That's pi radians. And the point right there is negative 1 comma 0. And because tangent is y over x, that's 0 over negative 1, which is just 0. So tangent of pi here ends up being 0 plus 1 plus c. So 4 equals ln of 1 plus c. So that means that 4 is equal to c. Okay. And now what we can do is rewrite our initial equation right here now that we know what c is. So I'm just going to go down here and completely rewrite it. R of t equals ln of tangent of t plus 1 plus 4. Okay, there we go. Happy day. Let's go on to the last one here. This has to do a little bit with derivatives. What we want to do is find and classify the relative extrema. So this will involve taking a derivative and then doing something with it in order to find where the possible humps and troughs are on this function's graph. Y equals ln of x squared plus 2x plus 3. If you want to go and give it a shot, you can start right now. Okay, so to find relative extrema, we're going to start by finding critical points. In order to find critical points, we start, of course, by taking the derivative. So I'm going to find dy dx here. Now, this particular function needs a rule in order to derive. If you know what rule we need to derive, you can say it out loud right now. It is the chain rule. Love it. Especially love the chain rule with natural logs. It works out really nicely. So the derivative of the inside here, the derivative of the inside of the function, will end up being 2x plus 2 times, then the derivative of the outer layer, which is ln of something, it's 1 over, and then we keep the something the same. So this derivative ends up being 2x plus 2 divided by x squared plus 2x plus 3. So that's our y prime. Now, to find relative extrema, what we want to do is we want to know where is the slope equal to 0 and where is the slope undefined. Those are the two places that we want to know about this. Now, to set the slope equal to 0, we set the top equal to 0. I'm just going to make a little division over here. So the slope equals 0 means that we take the numerator and find when that's 0. Looks like it's at x equals -1. Now, in order to find where the bottom is equal to 0 here, well, that would be the undefined part, but let's think about that for a second. If we were to go in and find where x squared plus 2x plus 3 equals 0, if it even has any places, that would mean that the inside of this natural log is 0. Now, if you've got a calculator next to you, you can try taking the natural log of 0. And the calculator will actually yell at you because there's an error. Now, that means that this function is not defined for when the inside of it is equal to 0, which means it's not possible for any relative mins or maxes to happen when the bottom of this derivative is 0. So we don't have to worry about this case. However, it's always good to think about when the slope might be undefined because you might end up having a relative max or min that actually is a cusp like this. That does happen from time to time. So let's keep on going with this path right here. X equals -1 is what we call a critical point. So we're going to take this critical point. We don't know whether it is a local max or a local min. It could be either one of those, or it could be neither. But let's make a little test and let's find out. So I'm going to make a little number line here. And I'm going to call this number line y prime because I'm investigating the derivative to see what this critical point is. Is it a local max or is it a local min? And I'm going to plot -1 on here. And let's just see what y prime does before and after this. So if I plug -1 into my derivative, so my derivative, we want to plug a number before -1 in. Let's say -2. So if I plug -2 into the derivative, I get 2 times -2 plus 2 over -2 squared, which is 4, minus 4, because 2 times -2 is -4, plus 3. This ends up being a negative number over, and then 4 minus 4 plus 3 is a positive number. Negative divided by a positive is a negative. So this value of the derivative on this side is negative. Of course, our critical point, the derivative is 0 there. Let's see what happens after that. So let's try the number 0. Let's plug 0 into our derivative. So we're doing 2 times 0 plus 2. You can probably do some mental math. You can probably do mental math on the bottom, and when you plug 0 into the bottom, you get 3. So this ends up being positive number over a positive number, which is positive values. So you can see here that our derivative, y prime, goes from negative to positive, meaning that our critical point here is actually a local min. And then always with a reason, because y prime switches from negative to positive. What a good reason. All right, that's a little bit of calculus with some natural logs. I hope this might help you guys out if you're having a little bit of trouble with it, and I'm hoping to get one of these videos done every week. Okay, thanks guys.